Alright, in section 2.5 we talk about continuity. Continuity just allows us to be able to, if we know that a function is continuous at a number a, then we can just use direct substitution, that the limit equals f of a. So it's very nice if we can show continuity first, and then we can just do direct substitution to find the limit. Now what does this definition mean? It means that f of a is defined. It means the limit exists, and they equal each other. A continuous function has a property that a small change in x produces only a small change in f of x. And so as you approach from either direction in small increments, you approach some y coordinate in small increments as well. And we say that f is discontinuous at a if it is not continuous at a, meaning if it fails on any one of these three, it's discontinuous. So now they talk about physical phenomena that are typically continuous, such as the velocity of a moving car. It changes gradually, smoothly. Or a person's height changes as well. There's discontinuity in nature, such as the electric current. It's either flowing or it isn't, so it's on or it's off, and that's definitely discontinuous. Geometrically, you can think of a function that is continuous for every number in an interval of a function whose graph has no breaks in it. The graph can be drawn without removing your pen from the page. Now, if you look at this figure 1, you can see how you can draw that in one stroke of your pen. Figure 2, you've got a number of breaks here, 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 and so it clearly has discontinuity in certain places. So let's look at it. Show where it's discontinuous and why. Well, the first one is at a equals 1. At 1, you got a limit approaching from either side, but it's not defined at the point. So for that reason, since f of 1 is not defined, it's discontinuous. What about at 3? Well, the limit from the left and the right don't agree, even though the f of 3 does exist. Since the limits from the left and right don't agree, then you can say that there's discontinuity at 3. Then what about at 5? Even though it is defined at 5, you must have the left and right-handed limits are equal, and they equal what f of 5 is, and they don't. So that one is not continuous, or is discontinuous. So they ask, where is this discontinuous? Well, you'd see where you're dividing by 0, so at 2. f of 2 is not defined, so it's discontinuous at 2. For b, where is it discontinuous? Well, at 2, you got problems there. Down here at the bottom of the page, they show what each one is. The first one, this is the graph of the first one we talked about. It is not defined at 2. And then this one, we have a problem at x equals 2 because the limit does not equal f of 2. So as you approach 2 from the left and right, you do get a y coordinate, but actually at the point 2, you don't get the same number. So they're not, it's not continuous, it's discontinuous. C, the limit of the function does not exist because you're shooting off to infinity in both directions. Remember, there's such a thing as an infinite limit, but it's technically a limit that does not exist. Alright, so you'd say you have discontinuity or infinite discontinuity at 0 there. These two are removable discontinuity because you can actually take one point, redefine it, and it becomes continuous again. And then this last one, the function of 1 over x, or function of greatest integer function, says that if you're at 1 or anything less than 2, you just type in for y coordinate 1. If you're at 2 or anything less than 3, your y coordinate is 2. And so it acts like a stair, and it has a break at every integer. So it is discontinuous. Now what does it mean to say something continuous from the right or left? It means that the right limit equals f of a, or the left hand limit equals f of a. So you can have continuity from the left, you can have continuity from the right, and you can also have continuity at some number a. Alright, so a function is continuous on an interval if it is continuous everywhere in the interval. And so what we're going to find is that we're going to hopefully prove that something is continuous over an open interval, and then we'll consider the endpoints. So the first thing they do is they say since this is a root and a polynomial, you can write this as, well, not because of that. You can just take the limit of the function equals the limit of these two, and you can break it up into two separate limits, and then you can bring the limit underneath, and then you can finally do direct substitution, and you get this, which is actually equal to f of a. So between minus 1 and 1, you have continuity at a. Now what about at the endpoints? Well, you look at it from the left, and if you look at it from the left for this guy, you see that it approaches the y coordinate of 1, which is f of negative 1. Then if you look at 1, this is from the right, sorry. If you look at a positive 1 from the left, you're coming in this way, it equals the y coordinate of 1, which is what f of 1 equals. So it's continuous at both endpoints and at every point in between, so you can say it's continuous over the closed interval minus 1 to 1. So what can we say now? We can say if f and g are continuous at a, then f plus g is continuous, f subtract g is continuous, c times f is continuous, f times g and f divided by g, where g is not 0, are all continuous. Okay, so we can also say that any polynomial is continuous everywhere. That is, it is continuous on the entire number line. And any rational function is continuous wherever it is defined. That is, on its domain it is continuous. So you need to find out where it's not defined, typically division by 0 or negatives under the square root. They talk about some phenomenon in the physical world. They talk about the volume of a sphere changes continuously with its radius, because this is a polynomial function. Likewise, a ball being thrown in the air with initial velocity is shown like this, again, a polynomial function, so the height of the ball is a continuous function of the elapsed time. Alright, so what if we want to do this one, the limit of this guy? Well, you're looking at it and you try and figure out where it is defined, and you worry about the denominator equaling 0, and the number that you want to throw out of your number line is 5/3. So your domain is everything except 5/3. Now we're not approaching 5/3, we're approaching -2, so we can do direct substitution and we get our answer right off the bat. As long as our number we're approaching is within the domain, we can use direct substitution for polynomials, rational functions, root functions, trig functions, logarithmic functions, exponential functions, and so on. It turns out that most of the familiar functions are continuous at every number in the domain. That gives some more examples. Sine, cosine are both continuous, and thus all the other trig functions are as well. And so they talk about tangent being sine over cosine, and so you watch out for division by 0, so you have trouble wherever cosine equals 0, and that's at pi over 2, 3 pi over 2, 5 pi over 2, and so on, plus and minus. The inverse function is the inverse function of a continuous one-to-one function is also continuous, and they say that it's intuitive because, remember, the inverse function is a reflection across the line y equals x, and the graph of the original function has no breaks in it, so the graph of the inverse function will not have any breaks in it. So it's intuitive that the inverse function is continuous. And so the inverse trig functions are continuous as well. And so we've got a whole set of functions now that we can just say are continuous for every number in their domain. That's the key part. You have to find out what the domain is and stay within it. Alright, so example 6, where is this function continuous? Well, its function is continuous everywhere except for x squared minus 1 equaling 0. So they talk about ln of x is continuous for x is greater than 0. That's the domain of natural log of x. And tangent inverse of x is continuous on everything. So if you were to add those two together, you consider the domains of both of them where they overlap, and so you're talking about greater than 0. The denominator is a polynomial, so it's continuous everywhere. And we have to worry about where the denominator equals 0, and thus we worry about where x equals plus or minus 1. So our domain here is greater than 0, but it can't equal 1 or minus 1, so we're talking about 0 to 1 and 1 to infinity. Nowhere else. Theorem 7, or by Theorem 7, sine is continuous, and in the denominator 2 plus cosine is continuous. Notice 2 plus cosine is never negative or 0, because cosine varies from minus 1 to 1. So this actually varies from 1 to 3. So it's never negative, so you don't have to worry about dividing by 0. Thus, this is continuous everywhere. It's defined by a continuous function. You can take the limit and you can do direct substitution and you get an answer. Another way of combining continuous functions is to get a continuous function is a form of a composite function. So if you got some function g and some function f and you do f composite g, that is also continuous. So here's one where they talk about arcsine of this thing here. If you can call this g and arcsine is f, this is just f composite g. Now how do they figure out what the limit is? Well, they bring the limit inside here, then they multiply it by the conjugate, top and bottom, or no, they factor the bottom, and then they cancel, and they get this guy here, and now they're able to do direct substitution, and they get 1/2 for this part, and arcsine of 1/2 is pi over 6. So, like I said before, if you've got two functions in f and g that are continuous at a, then you can say f composite g is continuous at a. So example 9, which of the following functions are continuous? Well, sine of x squared. You can let g be your x squared, and you can let f be sine x. So f composite g is continuous since both x squared and sine x are continuous. B, ln of 1 plus cosine. So we know that ln of x is continuous, and we know 1 plus cosine is continuous, so their composite function is continuous. We need to be careful about the domain here. The expression is defined when 1 plus cosine is greater than 0, so it's undefined when cosine equals -1, and this happens at all of the intervals of pi, 2 pi, 3 pi, plus or minus, and thus it has discontinuities at multiples of pi. And if you look at the graph, you can see there it's discontinuous at each of these intervals of pi, 2 pi, minus 2 pi, and so on. There's one last topic they talk about in here, the intermediate value theorem. All it says is if you got some value a and you got some value b, it creates some y coordinate f of a and f of b, and they have to be different. Okay. So then it says there's some number n such that when you plug a number c into the function, you get n, which is in between a and f of a and f of b. It basically means that if you're able to draw a line from some x value a to some x value b, and you pick a number between f of a and f of b, you're going to find a value for sure, guaranteed. Because if it's a continuous function whose graph has no holes or breaks, then it's easy to believe that the intermediate value theorem is true. And so here they talk about the intermediate value theorem. They talk about plugging in a 1 to the function and 2 into the function. 1, you get a negative number. 2, you get a positive number. So that means there has to be some number n that will give you some number that you can plug in here between 1 and 2 that will give you n equals 0. And so that is an idea of an intermediate value theorem. And they go a little further, make it even tighter and tighter, but it basically shows that there is a point where it crosses the x-axis where it equals 0.